Lions, skunks, and kangaroos, geo-distributed learning on the Flickr-Mammal Dataset. For full details on what I'm going to speak about today, please see our ICML paper, The Non-ID Data Quagmire of Decentralized Machine Learning. So the setting for today's talk is machine learning with decentralized data. As we know, pushing the training out to where the data are improves scalability, the ability to enforce data sovereignty, and protect privacy. However, there are a couple of challenges that arise in this setting. One is that now communication becomes a significant, even more significant bottleneck in the training. Unfortunately, there are a number of solutions that have emerged, such as federated averaging, Gaia, and deep gradient compression, that have reduced the amount of communication and helped eliminate this bottleneck. The second challenge, though, is that because the data is collected geo-distributedly, it has different distributions to it. Okay, so the data is non-ID across workers in this setting. Solutions is an emerging area. There are a number of solutions that are being developed, including what I'm going to present to you today. So in a nutshell, our contribution to the study of non-ID data in decentralized learning is threefold. First, we have curated a real-world data set that does exhibit the label skew that we're of interest in studying. Second, we've performed an experimental study on our real world and a bunch of synthetic data sets to show the extent of the problem and the challenge with non-ID data. And finally, we've presented some initial solutions to help with some of these challenges. So let's go to our real world data set. We call it Flickr-Mammal Dataset. What we've done is we've taken 42 mammal classes in the intersection of open images and ImageNet. And then we've used those classes to extract 40,000 images per class from Flickr. Okay, 4,000 images across each of 10 years. Finally, to remove the noise in our data set, for instance, that jaguar is not just is the animal and not a car, we run it through a neural network. And then we also do reverse geodecoding to tag each image with its country, subcontinent, and continent. The end result is a very nice data set, we believe, that has over 730,000 pictures with both the labels and geographic information. And that data set can be found at the URL shown here on the screen. So what do we learn from this data set? If you look at the top 3 mammals from each continent, you'll see they're completely disjoint. Okay, skunks are very popular. Images of skunks are very popular in the Americas, not so in other continents and so forth. And each of these top 3 mammals contributes between 44 and 92% of the total global images. So that, for instance, of all the images that include kangaroos, 92% of them come from Oceania. Looking at the full data set, we can see the distribution trends. Okay, so for each of the 42 mammals on the x-axis, the y shows the breakdown across continents of these distributions. And what we can see is that a vast majority of the mammals are dominated by just a few continents. So for instance, kangaroos, as mentioned, are dominated by Oceania, and skunks are dominated by the Americas, and lesser so by Europe. And if you look at the subcontinental level, the situation is even more highly skewed. Okay, so now that we've established that real-world data sets indeed have this type of skew that we're concerned with, let's highlight our experimental study. So in our experimental study, we looked at image classification and face recognition. We looked at 3 different decentralized learning algorithms: Gaia, federated averaging, and deep gradient compression. And we've looked at varying the amount of skew in the partitions. So here's our results for our curated Flickr-Mammal dataset. What we're showing here is the results for GoogleNet. Other neural networks are similar. And we're showing top 1 validation accuracy on the y-axis. And on the left side, what we're showing is artificially, if we just taken these images and shuffled them across the 5 partition, which represent the 5 continents, but we just thrown in IID, that's the results are as shown. Basically, the there's not a lot of loss involved in these communication efficient decentralized algorithms. Okay, on the right is the real data set. And what we see is that for BSP, which is the tightest of synchronization algorithms, basically you exchange gradients after every mini batch, retains its accuracy for this particular data set and this particular model. But because it's doing such heavy communications, heavy synchronization, it runs 20 times slower than our other two decentralized algorithms. Decentralized algorithms, on the other hand, with their less frequent communication, suffer significant accuracy loss. We've also looked at taking well-known data sets and synthetically partitioning them across the 5 partitions and measuring how well the different models do. So on the Cypher-10 data set, for instance, again, we have 3 different models, AlexNet, LuNet, and ResNet 20. And on the left of each of these is the shuffled data, so it's perfectly ID among the workers. And on the right is our artificially skewed data. And we can see that indeed there's a dramatic loss in accuracy across each of the 3 Gaia federated averaging and deep gradient compression methods that reduce communication. When we look at a different data set, ImageNet, we see the similar trends. And finally, we look at a different application like face recognition, we see the same trends. Okay, so what this tells us is that skewed data is indeed a pervasive and fundamental problem for these deep learning networks. Perhaps surprisingly, even BSP with its frequent communication loses accuracy in the cases where the DNNs have batch normalization networks, as batch normalization layers as shown in here for both ResNet 20 and ResNet 10. Okay, so let's drill down a little bit more on the batch normalization case. So batch normalization is a layer that you insert that has nice properties in training in general. And what it does is it looks at the inputs to that layer and it tries to produce a standard normal distribution out of them by looking at the mean and the variance and scaling them accordingly. And then at inference time or test time, you estimate a global mean and variance and you normalize according to that. And in IID data, this actually works very well. Okay, but the problem is with these skewed data sets, if you think about it, their individual mean and variance vary significantly from one partition to another, right? And so they're actually standardizing differently, right, in inconsistent ways. And as a result, that harms training, okay? And moreover, there's no sort of single global mu and sigma that work for all the partitions because they're different distributions, right? So after exploring a possibility for a lot of different alternatives to batch normalization, we discovered that group normalization, which was designed for a different purpose, is actually an effective replacement. So here we're looking on the at batch normal LuNet on the Cypher-10 data set. On the left is the original LuNet results, and on the right is the results where we replace the batch norm layers with these group norm layers. And again, the y-axis is top 1 validation accuracy. And here's what we see, right? So BSP, which suffered in the batch normalization case, now is not suffering anymore by skewed data. So the whole problem has gone away. And moreover, even for the decentralized algorithms that communicate less frequently, there's a reduction in the amount of accuracy loss they suffer. Okay, so now let's look at SkewScout. So SkewScout is our system level approach that tries to tackle these issues with the amount of skew in data and handling that. We have experiments in the paper that show that the degree of data skew determines the difficulty. Okay, we saw a little bit of this in that the real world data isn't quite as skewed as our synthetic data, and therefore the decline in accuracy, while significant, is not as dramatic as it is in the more significant skewed data. So what SkewScout does is it adapts the amount of communication to the skew-induced accuracy loss that's being observed as the training goes on. So let's consider a simple example here with just 2 partitions. Each of those partitions is training a model, and they're sharing parameters and so forth. But again, as we've seen in the skewed case, they're suffering. Okay, so what we do instead is that we periodically will send the model from one partition to another data set, another data center. And then that data center will look at this model it just received that was trained on this other worker's data and see how it's doing on its data. And if it's doing fine, then the assumption is that there's not a problem with this skew. And so it can continue to communicate less frequently. But if there is a problem, then it has to tighten the amount of communication and communicate more frequently. Okay, so basically the idea is we only want to communicate as much as necessary, and note that this is agnostic to the actual decentralized learning algorithm you use, as long as there's a knob in which you control communication. So how does this do? So what we're showing here is the communication savings over BSP, the multiplicative factor of that. We're showing it for the Cipher10 data set running AlexNet. And the reason we're focused on communication savings is that all data points achieve the same validation accuracy. So there's no difference in accuracy at all. All right. And what we're showing is 3 different levels of skew. 20% skew, which means 20% of the data is partitioned by label, and the other 80% is just randomly scattered, up to 100% where 100% of the data is partitioned by label. What we see is for SkewScout, it's able to have significant savings over BSP. 34%, factor of 34 savings in low skew, and even in 100% skew case, it's still able to save almost a factor of 10 in communication. We also compared against an oracle, which repeatedly tries out different amounts of communication and ends up selecting the best possible choice. And we can see that we're doing well relative to that, even to that oracle. Right? And similar results for GoogleNet. Okay, so the bottom line is that we're able to have significant savings over BSP, and we're within 1.5x of Oracle. Even though Oracle gets to do multiple runs and pick out the best possible communication thing for the particular data set you're seeing, whereas SkewScout just does this all in the context of a single run. So, key takeaways from this talk. First, we have curated this Flickr-Mammal Dataset, which shows that indeed in the real world, there's highly skewed label distribution, and it's available for people to study. We've shown that on both the real world data set and known data sets that we synthetically skewed, the skewed data is a pervasive problem, and that batch normalization is particularly problematic. Finally, we developed SkewScout, which adapts the decentralized learning to the amount of skew and can tailor the amount of communication savings to the actual amount of skew that you're observing. And that group normalization is a good alternative to batch normalization. So I just want to leave you with a few discussion questions. First, that SkewScout is a system solution to this problem. And so therefore it's complementary to recent work that's looked at the actual changing the algorithms to adapt to non-ID data. Second of all, there's this issue with objective functions, okay? Prior work has typically looked at an objective function that considers the union across the data across all the partitions. And the issue there is that, that's a very global view of the objective. And therefore, the majority trumps the minority, and minorities can suffer, right? The distributions that are less common will do less well. On the other hand, if you take it to the other extreme and do things too locally, for instance, just really focus on training a good private model each of the workers, then you have things like the lions, skunks, and kangaroos problem that the title hints to. All right, and this problem is that even though my local model has not seen any images of lions, skunks, and kangaroos, if a lion were to escape from the zoo here in Pittsburgh, I really would want my model to recognize it. Okay, so too local is also a problem. Finally, I want to note that label skew is only one form of non-IDness, so when we study in this paper, but more data sets and more study is needed on other forms. And in particular, because we believe that there are some subtleties there between different forms of non-IDness and how they need to be handled. And with that, I will take questions.